So this is our fourth class in partial differential equations. But as I pointed out several times, you can't do partial differential equations without knowing a little bit of ordinary differential equations. So we're taking off a couple of weeks to look at ODEs, ordinary differential equations. And in our last class, we worked out the general method to solve any first order linear ordinary differential equation. And we're using some pages from a book by Tom Apostle, which I posted on Blackboard and emailed out to you. And the first set of homeworks are on page 311. Are there any questions about any of the work we've done so far on first order linear differential equations?
Yes, the number 3 exercise involve trigonometry functions. So I would like to see what is the solution.
I'm sorry, so
I'm referring to the exercise.
which page?
3.
On page 11, number 3?
Right.
Y prime plus y tangent x equals sine 2x?
Right.
Okay. So,
Thank you.
yep. So this is homework on page 311, number 3, and we have an initial value problem connected to the linear differential equation, first order, y prime plus y times tangent x equals sine of 2x on the interval from minus pi over 2 to plus pi over 2, and satisfying the initial condition that y equals 2 when x equals 0. So a general form of a first order linear differential equation is y prime plus some function of x times y equals q of x. So in this case, my function p of x is tangent of x, and my function q of x is sine 2x. Well, one of the advantages of doing homework or working at home is you don't have to memorize everything. You can just look up the formula that we've derived, but hopefully you understand the derivation, you understand where everything comes from. So if you look at theorem 8.3, what is the formula for the solution of such a differential equation? So in the notation, a is equal to 0, b is equal to 2. When x is equal to a, y is equal to b. So when a is 0, b is 2. And the solution is of the following form. F of x equals b e to the minus a of x. That's actually a solution to the homogeneous equation if you had q of x equal to 0. Plus e to the minus a of x, integral from a to x, q of x, q of t, e to the a of t, dt, where what is a of x? A of x is the integral from a to x, a is 0, the integral from 0 to x of p of t is tangent t dt. Okay. So the first thing you need to do is calculate the integral of the tangent. So some people can remember these things. I never can. What is the tangent? It's sine t over cosine t dt. So if we make the substitution, u equals cosine t, so du dt is minus sine t. This is equal to the integral sine t dt is minus du over u. And when t is 0, cosine of 0 is 1. When t is x, this is cosine x. So this is minus the integral from 1 to cosine x du over u. This is just the logarithm. Minus the log of u from 1 to cosine x. So that's minus cosine minus the log, oops, of cosine of u, evaluated from 1 to, oh, sorry, I just wrote that, minus log of u. So this is minus the log of the cosine of x plus the log of 1, which is 0. And you can check if you differentiate this, you get 1 over the cosine times the derivative of the cosine, which is minus the sine. So you get sine over cosine or tangent. So a of x is the log minus the log of the cosine. And our a of x always comes up in the form of e to the a of x. So e to the a of x is e to the minus the log of the cosine. Notice we're only looking at the interval from minus pi over 2 to plus pi over 2. And in that interval, minus pi over 2 plus pi over 2, cosine is positive. So we don't have to worry about having a negative value for the argument of the logarithm. And e to the log of anything is the anything. This is 1 over cosine x, or if you prefer to write secant x, that's okay. Oops. Yeah. E to the a of x is 1 over the cosine. E to the minus a of x is cosine of x. Okay. Any questions so far? This is the beginning.
Professor, I'm using a method that I previously learned from that.
I'm sorry, you're using what?
I'm using another method that I learned from the previous class. So,
well,
I mean,
no one cares what method you use to solve the problem. People only care that you can solve the problem.
So on the test, if I'm using my method, it's all right?
Any method that gives you the answer is okay.
Okay, okay.
All right.
I gotta like take that off like every time somebody talks.
I'm sorry, what are you saying? What are you asking?
Oh, I'm sorry. I thought I was on mute. Sorry.
Oh, okay. Yep. All right.
Also, Professor, number 13.
Wait. I haven't solved the problem yet.
Oh, okay. Thank you.
I'm not even close to solving the problem. We have a lot more to do. So what I just showed is that e to the minus a of x is cosine x. So I need to compute what? So this is what the solution looks like. So I found e to the minus a of x, but I need to compute this integral, the integral of q of t e to the a of t dt. Right. So the integral from 0 to x of q of t e to the a of t. So that's the integral from dt. What is q of t? Q of t is the right-hand side, sine of 2t. What is e to the a of t? 1 over cosine t dt. I have to compute this trigonometric integral. Well, the easiest thing is to remember that sine of 2t is 2 sine t cosine t. So this is the integral from 0 to x of 2 sine t cosine t over cosine t dt. And the cosines cancel. So this is just 2 times the integral from 0 to x sine of t dt. And the integral of the sine is minus the cosine. So I have minus 2 cosine x minus minus 2, which is plus 2 cosine 0. Cosine 0 is 1. So this is 2 minus 2 cosine x. So if I put all this together, f of x is equal to b, that's 2, e to the minus a of x, 2 cosine x, plus e to the minus a of x, cosine x, times this integral, 2 minus 2 cosine x. Yeah, that's what it is. This is equal to 2 cosine x plus 2 cosine x is 4 cosine x minus 2 cosine squared x. So this is what is supposed to be the answer. Let's see. Now, what was our initial condition? F of 0 equals 2. If you plug in f of 0, you get 4 cosine 0 minus 2 cosine 0 squared. That's 4 times 1 minus 2 times 1 squared. It's 4 minus 2 is 2. So the initial condition is satisfied. So here I'm doing my check. And what about checking that this function really is a solution of the differential equation? So what is f prime of x plus f of x tangent of x? So this is my f of x. If I differentiate it, I get minus 4 sine x. When I differentiate minus 2 cosine squared x, I get minus 4 cosine x times the derivative of the cosine, which is minus the sine, makes this plus sine x, plus f of x, 4 cosine x minus 2 cosine squared x, times the tangent, which is sine x over cosine x. So this is minus 4 sine x plus 4 cosine x sine x. Cosines cancel, so I have plus 4 minus 2 cosine x sine x. So what is all this? I have 4 cosine x sine x minus 2 cosine x sine x. So that's 2 cosine x sine x, which is sine 2x. 4 sine x. And minus 4 sine x plus 4 sine x cancel. So I have sine 2x. What was my differential equation? This equals sine 2x. So this function I just calculated solves the differential equation and the initial condition. So,
Professor, this is non-homogeneous. So,
correct.
so if it wasn't homogeneous, equals 0, will be another equation that satisfies.
If it were non-homogeneous, the solution would just be 2 cosine x.
If it was an homogeneous.
Yeah, if Q of X were 0, this is the general formula for the solution. If homogeneous means Q of X is 0, that means this term disappears. It's just B cosine X. B cosine X. 2 cosine X would be the solution. The homogeneous is always much easier than the non-homogeneous.
Yeah, because I use an integrating factor to integrate it. So it's almost the same method I use.
Well,
It's very similar.
again, if you get the right answer, that's all that counts.
Professor, the last one, number 13, is too long, and it's like a proof, how to prove. I don't know how to do it. Number 13. This is the last one. Thank you.
Okay, let's take a look. Before I go on though, are there any other questions about this one? How to do this? Okay. So this is on page 312, number 13. Let's see what the problem says. Let K be a non-zero constant. Assume P and Q are continuous on an interval I. If A is an I and B is a real number. We're looking at the unique solution of the initial value problem. So the problem is V primes, find the function V prime, such that V prime plus K times P of X times V equals K times Q of X. That's our differential equation. And we want, so some solution is, we'll call G of X, and G of A is equal to B. This is the initial condition. So we have to show what? If n is different from 1 and k is 1 minus n, that means k is not 0. Prove that a function which is not identically 0 on I is a solution of the initial value problem without the k, if and only if the k power of f is equal to g on I. Okay, so we actually have to prove something here. So this is our starting point. We have functions p and q, and we have this non-homogeneous equation v prime plus k p of x v equals k q of x. And the unique solution of that equation is v equals some function g of x, unique satisfying this initial condition, g of a is equal to b. So let's suppose that f of x is a function which is g of x raised to the power k. Right? So this is half. We must show, this is called this part 1, must show that the function y equals f of x is a solution of the differential equation y prime plus p of x y equals q of x, satisfying the initial condition f of a is equal to b to the k. Sorry, f of a to the k is equal to b. So here we have this differential equation, and we want to show that this function is a solution. So if y is equal to, so this is v to the k. We'll just use that as sort of shorthand. So if y is equal to v to the k, then y prime, by the chain rule, is k v to the k minus 1 times v prime. So let's plug into this equation. Y prime plus p of xy is equal to k v to the k minus 1 v prime plus p of x times y, which is v to the k. I can factor with v to the k minus 1 out of that. Kv prime plus p of xv. Let's see. V is the solution of this differential equation. We let y be equal to v to the k. So dy dx is kv to the k minus 1 v prime. So let's see. So y prime plus p of xy, k v to the k minus 1 v prime plus p of x times v to the k there's something here doesn't look right to me.
Professor, that equation is non-homogeneous, right?
Oh, of course, yes. Q of
Okay.
x, it's not homogeneous because the right-hand side isn't 0. Let's see, let me look at it. Let me do it slightly differently. So cross this out. So we have this differential equation, and if we let v equal g of x is a solution to this initial value problem. And now we let f of x, oops, I'm sorry, I wrote this back. I keep writing this backwards. That's the problem. I want to let actually, I'm just going to start a new page. Good. It always helps to read the problem carefully and write it down correctly. So this is page 312, number 13, and we have the differential equation v prime plus k p of xv equals kq of x. And a solution is g of x. And this is a solution that satisfies the initial condition, g of a equals b. Suppose we let f of x be a function such that f of x to the kth power is g of x. And so what can we say then? So we know that g prime of x plus k p of x times g of x is equal to k times q of x. But g prime of x, this is the derivative of f of x to the k. This is k f of x times f prime of x. So if we plug that into this equation, we get k f of x times f prime of x plus k p of x times g of x, which is f of x to the k, equals k q of x. Oops. Derivative of f of x is k f of x to the k minus 1 times f of x, k minus 1. Divide by k, and factor out f of x minus 1. So you can cancel the k's. You get f of x to the k minus 1 times f prime of x plus p of x f of x equals q of x. So f prime of x plus p of x f of x equals q of x. Let me just bring this to the other side. This becomes f of x to the 1 minus x. Oops, sorry, to the 1 minus k. Oh, that's what we wanted to prove. Right? So f of x is a solution of the ordinary differential equation y prime plus p of x y equals q of x y to the n, where 1 minus k is the number we're calling n. Right? So let's look at this again carefully. The k be a non-zero constant. Let k equal 1 minus n. Prove that if g is a solution of this differential equation, and you let f be equal to f of x to the k, then you get a solution to this differential equation. Okay? So that's half of the problem. Right? This is part 1. Right? So if g of x solves this differential equation, then f of x solves that differential equation where n is defined to be 1 minus k. Are there any questions about that? What is this called? Oh, it's called mathematics, yes. So if you have a solution of this differential equation, then you get a solution of this one. And part 2 is the converse. So just take a clean piece of paper for that. Suppose we let y equal f of x be a solution of the differential equation y prime plus p of x y equals q of x y to the n. By the way, this is a nonlinear differential equation. Because you have a power of y occurring there. Right? This is a nonlinear differential equation. Suppose we let v be the function g of x. The f of x to the kth power. So let's compute g prime of x plus k p of x g of x. So if g of x is f of x to the k, g prime of x is k, f of x to the k minus 1, f prime of x. So this is k, f of x to the k minus 1, f prime of x, plus k p of x g of x, which is f of x to the k. Then we factor out k f of x to the k minus 1, and I get f prime of x plus p of x f of x. But f of x is a solution of this equation. So y prime plus py, or f prime of x plus pf, this is equal to q of x, y to the n, f of x to the n. What is f of n? N again is 1 minus k. F of x to the 1 minus k. F of x to the k minus 1 times f of x to the 1 minus k, they cancel. This is just equal to k q of x. So therefore, g of x is a solution of the equation v prime plus k p of x v equals k q of x. And we're done. So that, yeah, that's how you solve problem 13. You have to do a little bit of work. Are there any questions about that?
Thank you, Professor.
Any other questions about problems on this homework set? Okay, so we just studied linear first order differential equations. And now we want to study linear second order differential equations. For those of you who study some physics, you'll know that these come up constantly in physics. Acceleration is a second derivative. So a second order linear ordinary differential equation in its simplest form looks like second derivative plus some function p1 of x y prime plus p2 of x y equals q of x. This is a second order, and I'm assuming that you can divide through by whatever is the coefficient of y double prime. So this is just y double prime multiplied by 1. So you have the second derivative, the first derivative times a function of x, the function times a function of x equals some q of x. So this is second order and linear. And this is homogeneous if Q of X is 0 and non-homogeneous otherwise. Now we're going to look at really the simplest case of this. Constant coefficients. That is, P1 of X is some constant A, and P2 of X is some constant B. So these functions are constants, they're not varying. So the first thing we're going to do is look at second order. So you have second order differential equations. The simplest case is linear. An even simpler case is homogeneous. An even simpler case is constant coefficients. So we're going to try to solve, first of all, a differential equation that looks like y double prime plus ay prime plus b equals 0. Okay. Y double prime plus ay prime plus by equals 0. A and b are constants. Okay. So the first thing we're going to do is, well, actually not the first thing, but we want to solve a second order equation with constant coefficients. And the first thing we're going to look at is the special case when a is 0. So our equation is simply y double prime plus by equals 0. And you know from calculus what a solution is. So there are three cases. The simplest case is b equals 0. In that case, we're just saying we have a function whose second derivative is 0. That means the derivative of the first derivative is 0. That means y prime is a constant. And if y prime is a constant, that means y is constant times x plus another constant. So if b equals 0, the solution is a linear function, and every linear function is a solution. Oops. So this is really an if and only if statement. So we just found all solutions in the case y double prime equals 0. Okay. Suppose we have, so this is case 1. Case 2, sorry. This is the special case. Case 1 is when b is 0. Case 2 is when b is, well, positive or negative. So let's say case 2 is when b is negative. So this means we have y double prime. If b is negative, you can write it as minus something that's positive, and anything that's positive is positive. It's minus something positive, and every positive number is a square. So we're looking at the equation y double prime minus k squared y equals 0, or y double prime is k squared y. And we know two obvious solutions. One is e to the k times x, because if you differentiate this twice, you get k squared times e to the kx, and e to the minus kx. If you differentiate this once, you get minus k e to the minus kx. Differentiate it a second time, you get k squared e to the minus kx. And if you multiply these by any constants, these are also still solutions. And if you add them, you get a solution. So any function of this form is a solution. This doesn't say that every solution is of this form. It says that every function of this form does solve this differential equation. In fact, we'll prove that every solution must be of this form. But that takes a little bit of work. All right, so we have the equation y double prime plus by equals 0. We have the case b equals 0. We have the case b negative. So the third case is b is positive. So b is, you can write b as the square of something positive. So this is the equation y double prime equals minus k squared y. And again, you can check that one solution is cosine of k times y. If you differentiate this once, you get minus k sine ky. Differentiate it again, you get minus k times k cosine y, minus k squared. That's the solution. And sine of ky, sorry, this is x. Cosine kx and sine kx, these are both solutions of this equation. If you multiply these by any constants, you get a solution. And if you add them, you get a solution. So for any numbers c1 and c2, this function, this linear combination of cosine kx and sine kx are solutions of the differential equation. And again, it turns out every solution of this differential equation is a function of this form, and we will prove that. We will prove that. Right. Now you can say, fine, if you're looking at second order equations with constant coefficients, they're pretty simple to begin with, and you made it even simpler by assuming a equals 0. But what about the case when a is different from 0? And the answer is, to that question, you can reduce every differential equation with constant second order constant coefficients to one where that middle term, a, is equal to 0. Right? And the way we do that is the following, I don't know, trick, if you like. So we have this equation we want to solve. Y double prime plus ay prime plus by equals 0. And suppose we let y be the product of two functions, u and v. So if you let y equals u and v, u times v, y prime is u prime v plus u v prime, and y double prime, when you differentiate this, you get u double prime v plus u prime v prime. When you differentiate this, you get u prime v prime, so I have two of these, plus u v double prime. So let me plug this into my differential equation. Y double prime plus ay prime plus by is going to be the second derivative, u double prime v plus 2u prime v prime plus u v double prime plus a times y prime, u prime v plus u v prime plus b times y, which is b times u v. Now, I have some terms that just involve a u here. Here there's a u, here there's a u, and here there's a u. So let me take those three terms and factor out a u. So this is v double prime plus av prime plus bv times u. And then I have some terms that involve u prime. Let's see. Here there's a u prime, and here there's a u prime. So I have plus 2v prime plus av times u prime. And then I have one last term, which is v u double prime. Now, coefficient of u prime is this. Suppose I can choose v so that 2v prime plus av equals 0. That's the same as the differential equation v prime, well, 2v prime equals minus av. And if I divide by 2, I get v prime equals minus a half v. But we already solved this first order equation when the derivative of a function is proportional to itself. A solution of this, one solution is v equals e to the minus a over 2x. So if I and which is never 0. So if I look for a solution y equals uv, and v is equal to this, and I plug it into this equation, let's see, what do I get? If v is minus a over 2x, v prime is minus a over 2 e to the minus a over 2x, or minus a over 2v, and v double prime is minus a over 2 times minus a over 2 e to the minus a over 2x. When I multiply this, I get a squared over 4 times v. So this equation becomes what? V double prime plus AV prime so y double prime plus AY prime plus BY equals. So V double prime plus AV prime plus VV, this is A squared over 4 times V plus AV prime minus A squared over 2 times V plus B times V times U plus, this is 0, V times U double prime is 0. What is this? This is minus A squared over 4. Or this is the same as 4b minus a squared over 4. V is an exponential. V of x is different from 0 for all x, so I can divide by it. So what I get is this a differential equation, u double prime, I'm dividing out by v, plus 4b minus a squared over 4u equals 0. So let's go back and just make sure it's clear what's going on. Here's my second order, linear, homogeneous, ordinary differential equation with constant coefficients a and b. I want to show I can reduce this to another second order equation in which the middle term disappears. And we can do that as follows. I'm going to look for a solution of the form y equals u times v. I mean, every function is a product of two functions. I mean, you know, f of x is e to the x f of x times e to the minus x. I mean, so this is no real restriction in any way. Suppose we're at y equals uv. I want to choose v in such a way that I get a new and simpler equation. So if y is this product, here's y prime and y double prime. We plug it into the differential equation, this is what I get. I want the coefficient of u prime to be 0. That means I want this first order differential equation homogeneous. I want v to be a solution of that. And there is a solution. This is the solution. I mean, if a is 0, this is just 1. It's not very, but if a is 0, we already have a equals 0. If you let v equal e to the minus a over 2x, then you will have a solution y equals u, v is e to the minus a over 2x times some function u of x, where u of x solves this equation. And we just saw how to solve this equation. It's either linear or a sum of exponentials or a sine plus a cosine. So now we can solve every second order constant coefficient homogeneous ordinary differential equation. And the hard thing is uniqueness. And it's also the most interesting thing.
Professor, that term uniqueness.
Excuse me?
That term uniqueness implies many infinite solutions.
I don't understand your question. Uniqueness means if you take the differential equation with some initial condition, there exists one and only one solution. So there are not infinitely many different solutions. Once you have an initial condition, there's exactly one solution.
So why is you mentioned is can be difficult to be unique? Can you explain the reason behind?
Wait, again, I don't understand your question.
Okay, you're saying uniqueness, only unique.
I haven't proved it, but I'm claiming the theorem, which we will prove, but maybe not today, maybe next Monday, is that the solutions of these differential equations are unique. There's only one solution. If you have an initial condition, there's one solution that solves the differential equation and satisfies the initial condition. So let me state the uniqueness theorem. So in the notes that I sent out, this is on page 326. There are two theorems, and I'll state both of them. Theorem 8.6. So this is for the differential equation y double prime plus vy equals 0. Okay. So given a real number b, we can define two functions, u1 of x and u2 of x, on the interval from minus infinity to infinity. That means for all real numbers, as follows. So there are three cases again. If b is 0, then we can let u1 of x be equal to 1 and u2 of x be equal to x. These are both solutions of the equation. If b is negative, then we can write b as minus something positive, and we let u1 of x be equal to the cosine of kx, and u2 of x be equal to the sine of kx. And in the third case, if b is positive, then we can write b as plus k squared, and we can let u equal oops, I'm sorry. This was the case. I reversed this. So let me just do it in the same way the text does. If b is negative, and you can write it as minus k squared, this is e to the kx and e to the minus kx. And if b is positive, we're going to get sines and cosines. You let u1 of x be equal to cosine of kx, and u2 be equal to the sine of kx. So then every solution of the ordinary differential equation y double prime plus by equals 0 has the form y equals c1 u1 of x plus c2 u2 of x. So not only is every linear combination of u1 and u2 a solution of the differential equation, but every solution is of this form. Okay.
Professor, what about the existence? Because you define uniqueness right now.
No. So we already showed that these differential equations have these solutions. If b is 0, you have a linear function, a combination of 1 and x. If b is negative, you have a linear combination of these two exponential functions. If b is positive, you have linear combinations of these trigonometric functions, sines and cosines. And we already showed that each of these linear combinations is a solution of the ordinary differential equation. The uniqueness theorem says that every solution of the differential equation must be of this form. So we have all the solutions. And for any initial condition, you can always find constants C1 and C2 that satisfy the initial conditions. Let's just look at an example. Suppose you had the differential equation y double prime plus, I don't know, minus 25y equals 0, and we want a solution where y of 3 is equal to 11. Okay. So here's our differential equation. B is minus 25, which is negative. You can write that as minus k squared minus 5 squared. K is equal to 5. A general solution is y equals c1 e to the 5x plus c2 e to the minus 5x. So we have some function f of x of this form. And we need two initial conditions for the function, and let's say y prime at 3 is equal to minus 2. Right? So can we find a solution that satisfies these initial conditions? So this is f of x. F prime of x is 5c1 e to the 5x minus 5c2 e to the minus 5x. So f of 3, when you plug in x equals 3, you get e to the 15x times c1 plus, when you plug in x equals 3, you get e to the 15 c1 plus e to the minus 15 c2 is supposed to be 11. F prime of 3, when you plug in x equals 3, you get 5 e to the 15 c1 minus 5 e to the minus 5, minus 5 e to the minus 15 c2 equals negative 2. What do we have here? Two equations and two unknowns, linear equations. And the determinant, see, these are the coefficients. You have e to the 15x, e to the 15. These are all 15s. E to the 15, e to the minus 15, 5e to the 15, minus 5e to the minus 15. You take the determinant of this 2 by 2 matrix, you get minus 5, which is minus 10, which is different from 0. And when you have two equations and two unknowns, if you write down the matrix of the coefficients of the unknowns, if the determinant is different from 0, you can solve these equations. These are two linear equations. So there is a solution, always. And in the homework problems, you'll have to compute some. Now, when you put all this together for the second order equation with a and b, a not necessarily 0. So here we have the second order equation, homogeneous, second order, linear, constant coefficients. You have to look at what's called the discriminant of the equation, a squared minus 4b. And remember, when we reduced this to the simpler case, we had the second order equation. This is minus the discriminant, 4b minus a squared. Right? Everything depended on what this was. So when you put everything together, the theorem, so this is theorem 8.7 on page 326. So let D be equal to the discriminant, a squared minus 4b. So every solution of this differential equation on the whole real line has the following form. Y is equal to e to the minus ax over 2, c1 u1 of x plus c2 u2 of x. where u1 and u2 are determined as follows. So again, it depends on whether the discriminant is 0, positive, or negative. So if d equals 0, then u1 of x is 1, and u2 of x is x. If d is positive, then u1 of x is e to the kx, and u2 of x is e to the minus kx, where k is equal to 1/2 the square root of the discriminant. And if d is negative, then we have u1 of x and u2 of x are the cosine and the sine. Cosine kx u2 of x is sine kx, and k is 1/2 square root of negative d. D is negative, so minus d is positive, and you can take the square root. So this is a complete solution to second-order homogeneous linear differential equations with constant coefficients. But the only way to understand this is to do a lot of problems.
Professor,
Yeah,
I just want to make sure, in the example when d equals 0, u2 of x equals y, or you said 0?
X. No. This is x. 1 and a. This is just the these are just the solutions of y double prime equals 0. You have 1 and x are the two solutions in every linear combination of them. Every linear equation, a plus bx, is a solution. Now, let me do an example. Let's try and make it an interesting example. So this is one of the homework problems. So this is on page 328, number 5. Y double prime minus 2y prime plus 3y equals 0. So the coefficient of y prime, a, is -2. The coefficient of y, that's my b, is 3. The discriminant, d, is a squared minus 4b. That's 4 minus 9 is -5. Oops, let me see if I did this right. 4 minus, oops, so a squared minus 4b. This is -2 squared minus 4 times 3 is 4 minus 12 is -8. So this is minus k squared. So k squared equals 8. So k is the square root of 8, which is 2 root 2. And k over 2 is the square root of 2. Oops. Let me write this correctly. This is D. And K is 1/2 the square root of minus D, which is 1/2 the square root of minus 8, which is 1/2 of 2 root 2, or the square root of 2. So K is the square root of 2. So what is the general solution? A is minus 2. So the general solution, we have two functions. So e to the minus ax over 2 is e to the minus 2x over minus 2 is just e to the x. So we have e to the x cosine of kx and e to the x sine of kx. And every linear combination of them. So it's really factor out the e to the kx. So the general solution is y equals e to the x, some constant times c1 cosine kx, cosine 2x, plus c2 sine of 2x. This is the general solution of, square root of 2. That's the general solution of the differential equation. In problem 5, yeah, they just want the general solution. That's it. Right? Any questions about that? Let me do another one. This is not part of the homework. That's okay. Number 8. Oh, let me say one other thing, which is important administratively. So as you know, by around the 3rd week of the semester, the college has to know whether you've attended, there's a requirement of the state of New York, whether you've attended any classes, at least one class so far. How do they interpret it when we're not meeting physically in a classroom? Attending class means having turned in at least one homework. So you have to make sure that by next week, you have submitted at least one homework, at least something. Because the way that the college will determine whether you have been in attendance at all is to look at the homework section of Blackboard. And if there's no homework submitted at all, you'll be reported as never having attended. And that can mess up your registration and scholarship money and all sorts of things. So make sure that by Monday of next week, you've gone to Blackboard and submitted at least one of the 2 homeworks. Other than, if not, then you'll be in some trouble. So I'll send out an email to remind everyone about this, but it's an important thing to notice. Okay.
Professor, I submit the homework wrong, the wrong pages, so I can able to submit again. Because
That's fine. It doesn't have to be, the homework doesn't have to be correct. There just has to be something submitted in homework, right? No matter what it is.
I mean, I need to resubmit again.
You can submit homework as many times as you wish.
Oh.
The way the Blackboard is set up, if you submit a homework and it wasn't complete and you've done some more and you want to submit, you can resubmit the homework.
Oh, okay. I will do it.
Right.
Thanks.
So number 8 is y double prime minus 2y prime plus 5y equals 0. We want to find the general solution to this differential equation. So a is minus 2, b is 5. The discriminant, a squared minus 4b, is 4 minus 20, is minus 16. So k, which is 1/2 the square root of minus d, is 1/2 the square root of 16, which is 4 over 2, or plus 2. A is equal to -2, so e to the minus ax over 2 is just e to the x again. So we have as our general solution, y equals e to the x, c1 cosine of 2x plus c2 sine of 2x. So let's just check and see if I did this correctly. If this is y, when you differentiate, you get e to the x, c1 cosine 2x plus c2 sine of 2x plus e to the x times the derivative of this, which is minus 2 c1 sine 2x plus the derivative of this, 2 c2 cosine 2x. So this is e to the x times cosine 2x. I have a c1 plus 2c2 cosine 2x plus a c2 minus 2c1 sine of 2x. So y double prime is e to the x c1 plus 2c2 cosine 2x plus c2 minus 2c1 sine 2x plus e to the x times the derivative of this, which is minus 2 c1 plus 2c2 sine of 2x plus 2 c2 minus 2c1 cosine of 2x. That's equal to e to the x. And then what do I have times cosine of 2x? I have c1 plus 2c2 plus 2c2, that's 4c2, minus 4c1, c1 minus 4c1, minus 3c1, plus something times sine of 2x. I have a c2 minus 4c2, minus 3c2, and minus 2c1 minus 2c1, minus 4c1. So maybe this is correct. I have no idea. So let's plug these things into the equation. Y double prime minus 2y prime plus 5y equals. So I'm going to have e to the x times something times cosine 2x and something times sine of 2x. So what do I have times cosine of 2x? For y double prime, it's minus 3c1 plus 4c2 minus 2y prime, so that's minus 2c1 minus 4c2 plus 5y plus 5c1. That's all zero. That's good. And what I have multiplying sine of 2x? I have y double prime. I have a minus 4c1 minus 3c2 minus 2y prime. That's minus 2c2 plus 4c1 plus 5y plus 5c2. Again, this all cancels. I get 0. So we're good. The general solution of y double prime minus 2y prime plus 5y equals 0 is y equals e to the x c1 cosine 2x plus c2 sine of 2x. So we solved the differential equation. Any questions about this? You'll see in a couple of weeks when we go back to partial differential equations that in many cases, the way you solve the partial differential equation is by converting it to ordinary differential equations. But that only helps you if you can solve the ordinary differential equation. That's what we're doing here. Okay. Any questions? Okay. If not, that is it for today. And I will be back on Monday. So I will see you, talk to you then.
Thank you.
Bye, everybody.
Have a good one.
Yep, thank you. You too.